Laplace transform. Okay, so briefly, although it is not part of the subject, it is beyond the scope, we would like to apply Laplace transformation. Okay, the inverse and the Laplace transform. Okay, so what is the definition of the subject? Very simple. We have the system in time domain. We were solving the RL circuit in ordinary differential equation in its original sense, in the original function. We convert that, we solve the solution, no, in that case using the techniques, no, the variable separable in ODE, ordinary differential equation. Now in Laplace transform, we convert the system, the model, which is expressed by the I of t. In this case here, we have the x of t. Okay, so we transform that one into the frequency domain and solve the determine the solution or solve for the solution. And then when you get the solution here, okay, in the frequency domain, you inverse, no, you go back to the original domain. Okay, so that's the idea of the Laplace transform. Okay, so it's another, you can think it's another space. Okay, because later on you will see that the one that you're solving, the time domain, is really difficult, no, and the computers or any device cannot solve them analytically. So basically this time domain solution here can be solved mainly analytically, no. So here in the frequency domain, you can solve it numerically, no. So later on in your subjects, the major subjects, you might encounter numerical methods. So in this case, we just like to show, no, what is how we can use Laplace transform in this in solving differential equation. So these are the transformations. No, in your other subject, you will encounter Laplace transform in advanced engineering math. Okay, but here we just simply briefly use, no, the transformation, and later on in that subject you already have the idea, no, where and when you are going to use Laplace transformation. So uh, okay, so these are the transformation. Um, we can use this one later in our solution and derivation. Okay, so remember your RL circuit. We have a circuit, and then at time is equal to 0, and then it is closed, making it the current flowing at that instant. Okay, so what will be the behavior of your inductor? And we know that the ordinary differential equation, we have this expression. Now let us derive the same equation using Laplace transform. Okay, instead of the analytical method. But actually Laplace transform is also analytical, but because of its linearity, okay, because of its linearity, or you can think of it as an algebra. Okay, you can solve it numerically. Okay, so the first step, okay, so just to remember, you have the RL, and we're dealing with current. Okay, because the voltage you can solve through the current, and then also current is common to all of them, no, so that's why we solve current. So remember the KVL, Kirchhoff's voltage law, summation of voltages is equal to 0. In this case, the source is equal to uh, the one who receives, or the passive devices. In this case, the resistor and the inductor. Okay, so VR and VL is equal to BS. Now, since we're dealing with DC, take note, BS is a constant. Okay, VS is a constant. So later on in AC, you will be dealing with sinusoids. So that's why we go first to the DC, so that later on it would be easier for you to understand AC. Now we replace all the voltages with the respective currents, because current is common to all of them, and we only have one equation. Therefore, if you have one equation and one unknown, and which is current, then we can solve the problem. Okay, that's a very basic thing. One variable and one equation, you can solve the variable. Okay, so you have here for the voltage across the resistor, you have R times I, okay, Ohm's law. And then VL is equal to L di dt, okay. So the voltage across the inductor, or the induced voltage, which you will learn in and you will learn this thing in the electromagnetic class. Okay, so L di dt. Okay, so because of the changes of your current, there's an induced voltage. Okay, changes in current, you will have an induced voltage. So that's why di over dt, because it's a changes of current. No, that the change in current over time. Okay, it produces electromagnetic or sorry, induced voltage. Okay, and then you have the source Vs, which is still voltage but constant value, whatever value is that. Right? So you just put it as a arbitrary variable. Okay, but it's not our concern. So, but we know it's constant. Okay, and then you have that one and get the Laplace transform. So this is how we apply Laplace transform. Okay, so how to apply the Laplace transform? Okay, go back to the table. Okay. Uh, Okay, now for a now imagine our I of t is a variable. Okay, you can think of it as x. Okay, so Rx. Now in Laplace transform, the Laplace of Cx, okay, coefficient and x is equal to capital. Okay, so there's a difference between the time. No, the time is small case, and then for that frequency domain is in the capital case. No, x of s, and then you have the constant c. Okay, you can see this one from the previous slide. No, so here. Oops, sorry. Okay, so you have it. Okay, so where's the variable? I think it's not in the table. Okay, but take note of this, no? You have the number 1, so the transformation is 1 over s. But I think the variable is not here. But yeah, so because actually it doesn't change, no? The variable is still the variable. So that's the pretty common case, okay? And then for the derivative, you can recall from the table, you have LSIS. S is a somehow like a variable, no? It's like a frequency, no? So later on we will learn what is S, okay, in a physical sense. And then it's equal to Vs over S. Now saying Vs is a constant, so therefore Vs over S. Okay, so S is a variable. Okay, in that case. And then, so arranging the equation, removing the denominator of the Vs over S, multiplying all sides by S. So you will have Ls squared Is, okay, plus Rs Is plus Bs, okay. So you just multiply all of them with S, then you just arrange the equation, okay. We're not yet looking for the S, okay. Our goal is to find I of t, okay. So this is the first. We transform the time domain into frequency domain, and then you get the I of s, okay, and then you see Ls squared plus Rs is equal to Vs, okay. And okay, our goal is again to get the variable I of s, which is in the frequency domain and not anymore in time domain, okay. So then, okay, so you have here, no, sorry. So you have Vs over Ls times S plus R over L. So we just get the L and S outside, so that Ls times S plus RL. Now, there will be a technique we call the partial fraction, which you will learn later on. And here you can see that you need to make a two terms, okay, removing the 2s, no, because in this case you have s squared, right? Then you need to remove the two terms, the ls and then s plus rl, okay. So you will have this form. You should have that form instead of this form, no. So you have a plus or a over s plus b over s plus rl, okay. Now this is what we call the partial fraction, so removing the two, so that this one, if you inverse Laplace going back to the time domain, okay, easier, okay, instead of this one, okay. So later on you will see, no, how come it is easier. And then, okay, so how do we solve, okay, how do we solve a and b, because a and b are unknown yet, okay. Very simple. Okay, so you multiply. First thing, we need to solve for a. How to solve for a? You multiplied all the terms. Okay, this on the left and this on the right. You multiply them with s plus r over l. Okay, so if you multiply that one, and then let s is equal to negative r over l. So take note, this one came from here. Okay, the root negative rl comes from that. Actually, we call this one the root, no? In math, no? The root. Okay, s, actually s is equal to 0. 0 is a root. In this case here, negative rl, r over l is a root also. So changing s into the negative rl, okay, one of the root. So you will see that the b, no, when you multiply this term and this on both a over s and b over this thing, so this one will cancel out this thing. So that's why it becomes b. Okay, and then for a, so you have that one. Then if you put the s at negative rl, then this one becomes 0. So therefore a becomes 0. Okay, and also the same thing here when you multiply into is. If you multiply this one with this term here, so this will cancel out. Okay, so that therefore you have this term here. Okay, I hope you get the idea, no? Okay, and then you just simply arrange them. When you're changing, this one becomes 0, this one is removed from the equation, and then s changed to negative rl. Okay, because we change s, no, from this ls. Okay, now the s here is just a it's just a subscript. Okay, and then you can find b. Okay, b is simply negative vs over r. Okay, so b is negative vs over r. You know, vs and r, they are constants. Okay, r is coefficients in the previous equation. Okay, now we're down with b, and let's try to solve a. How to solve a? You know the denominator of a is s, so you multiply the equations with s. Okay, and let s is equal to 0. Okay, so you have that one. Okay, so when you multiply this one with s, cancel. You multiply s here, cancel. When you multiply s here, this becomes here. Now if you let s is equal to 0, then this one becomes 0. Okay, so I hope you see there's no s anymore here, and the denominator is cancelled. Okay, so we have this equation. Okay, and you arrange this equation, and then you will get vs over r. Okay, so because cancel l, cancel. Okay, so you have vs over r. Now we have a and b. So our a and b is vs over r and negative vs over r respectively. And take note here, why is it negative rl? Okay, so you just arrange actually, no? Oh, sorry. I think this one here, this is plus, but you will see that you have a formula in your table which is 1 over s minus a. Okay. Now having solved this, you can actually go back to the time domain. We are still in the s domain, or we call it frequency domain. So converting it back to the time domain, and we will have this answer. Okay, so this one here, if you notice, 1 over s, actually this is vs over r times 1 over s, and if you take the Laplace inverse of this is equal to 1. Okay, 1 vs times r, this is actually vs over r. Okay, take the Laplace inverse. Okay, so actually 1 over s, you just look at 1 over s, and then the Laplace inverse of this is 1. Okay, that's in the table, and then the Laplace inverse of um, 1 over s minus a is equal to e to the negative at. Okay, and then if you have a coefficient, which is in this case negative vs over r, so negative vs over r, so this is, you just multiply this one with vs over r, and this is negative. Okay, so therefore you have this equation. So I hope you get the idea, no?